Okay, in this wonderful section of our latest installment of videos of the class lecture notes, we're going to talk about the gas reaction stoichiometry. And what we mean by this is that we can use stoichiometry that we learned back in a couple of chapters ago, balanced equations, and using stoichiometry to predict the amount of materials that we can either make or get when we do a reaction, and predicting how much we're going to get or need to make our products or reactants. And we can use the ideal gas reaction, the ideal gas equation to make predictions on what the conditions are to from one set of conditions to the other conditions. And if you remember the ideal gas law, that there is a factor in there called N, and N is the number of moles, and coincidentally or fortuitously, that stoichiometry also uses as moles for the balanced equation. So we can use the combination of the two through the mole bridge to make predictions of gas reactions with both stoichiometry and the number of moles. So let's see how this works. So stoichiometry again is the math of the equations, right? The math of chemical equations, and the ideal gas law is the math of ideal gases, right? So if we know that, for example, in ideal gas law, certain conditions like P, V, and T will give a certain number of moles of a material based on the equation PV equals nRT. So if we have a pressure and we have a volume, we have a temperature, we know what the number of grams, we know the number of moles that particular gas at that particular set of conditions occupies. So we can make predictions on the number of moles, and then we can use the number of moles back into our balanced equation to make predictions on what we can do as far as products or reactants to make or decompose that gas or react that gas. So let's talk about those some more. So we use stoichiometry and the ideal gas law to make gas predictions, and then we use the gas law to make predictions on PV and N and T from a reaction, and then the balanced equation to make predictions on the amount of reactions or products to achieve these conditions. So basically what it starts out is we use the gas law. So if I give you P1, V1, and T1, we can know what N is, and we can use that from a gas reaction, and then the balanced equation to make predictions on the amount of reactions or products to achieve these conditions. It's a two-step process to solve, and the bridge is through the number of moles, or N, right? So let's write that down here. So let's just write the two equations here. So here we go, and equation 1, or we only need really one equation, so we have P V equals N, small n, R, big R, and then T, right, and T is always in Kelvin, so T equals K, right, and we know if we have a pressure here and a volume that we give a volume, we're going to be able to, and then temperature, we can make or predict the number of N, and N, remember, is the number of moles of the gas. Moles of gas. Okay, so if we know the number of moles of the gas, then what we can do, I'm just going to erase this part because the only part we need to know now is that N, right? We've already figured it out from this part of the equation, right? We've done the N. All right, let's do that real quick. Erase, keep erasing, and make the eraser a little bigger. Okay, so make the eraser a lot bigger. Okay, so now that we know the number of moles, let's go back and do, let's just look at a simple equation here where we have A plus B, and maybe that gives us C gas, right? And so let's say A solid, right, plus B gas gives us a C gas, all right, and then we'll put D solid here just to make it complete, right, or something. So if we know the number of moles of the gas, so that would maybe see that would be B, then we could predict the number of moles of C from that equation to make that gas based on the ideal gas law. So we'll show you a little bit more about this in a second. So if we know the number of moles of gas here, then we can make a prediction of the C gas, or we can make prediction of A, or we can even make prediction of D, based on from the moles from the gas from the ideal gas law. All right, so let's just erase all this. We're going to make an eraser here, and this, and D, and make this all go away. Okay, so let's just go to the next slide, and we'll show a little bit more of a demonstration of what I mean. Okay, so here's a simple equation here. We have nitrogen gas mixed with 3 moles of hydrogen gas, and we get 2 moles of ammonia, right? So remember, ammonia is NH3. And so the question to ask is, what volume of ammonia, is produced if 40 grams of hydrogen reacts completely with at 35 degrees and 142 kPa. So we now look at this and we say, well, we have grams of hydrogen, right? But our reaction here is in moles, right? We always have a reaction in moles. So this is always the, in moles. All right, gotta actually remember that I have to write the proper thing here. So that's always in moles, right? Okay, so that's always in moles, and we might make sure it's balanced. So let's just make sure it's balanced. All right, check balance, right? We always want to do that. So let's check balance right here. So we have 2N2. That's good. So that's 2 there, 2 N's. And on this side we have 2 N's, so that's good. And we have 6 hydrogens, 3 times 2, and then we have 2 times 3 here, so that's good. So everything checks out, so that's good. So that's a balanced equation, right? Don't assume that we give you a balanced equation. Always assume we don't, and just make sure it's balanced before you do anything. Okay, and then we're going to do here. So we just treat this like any other stoichiometry problem first. So the first thing is the stoichiometry part. So I'm just going to put it to stoic. Right, and then we just treat that as we would to any other stoichiometry problem. So we have 40 grams, right? That's my half, right? We always do the half first, and then 40 grams, and then that's going to be times some. Always put that over 1. I do, at least. And then we're going to have some types of thing here. 40 grams of hydrogen, so we need the moles of hydrogen, mole of H2, and we know that the moles of hydrogen, 1 mole of hydrogen weighs 2 grams, right? And then we have to multiply that by something else. That's our molar ratio to go from A to B, right? So we have to cross over from here. So this is our crossover. When we want to go to cross back forth here, we have to cross over from the 2 mole triangles, and it's asking me the volume of ammonia. Well, I can't calculate the volume directly from this, but I can calculate the number of moles. So we have to go here and put the 1 mole. Oh, actually, we don't put 1 mole. Again, we make a mistake. We want to make sure that we get the right ratio here. We're looking at 3 moles of hydrogen to 2 moles of ammonia, so we have to have 3 moles of H2, right? 3 moles of H2 over 2 moles of NH3. Right, so, and that's going to give me the number of moles of NH3. Number of moles of NH3. And remember that the number of moles is also going to equal to N in the ideal gas law. And N equals ideal gas law. N equal ideal gas law. Right? That's the N in the ideal gas law. I guess we should write it a little bit, like we normally do for the ideal gas law. And then we just put the little n. Okay? That's a little n in the ideal gas law. Okay? Let me write that a little better so it's kind of scribbly off the paper here. But that's the n that we're solving for, can be used now in the ideal gas law. So this is going to be the n equals ideal gas law. Okay, so that's the transition between the two. Like I said, it's two separate steps, but the n is the ideal gas law molar thing. So if we do all this, we should get 13.3 moles, if I did my math correctly here. Let's see here. 40 divided by 2 is 20. 20 times 40 is 80. That doesn't make sense here. Let's see. Oh, what volume is produced? Okay, so the number of moles, right? So we have 13.3 moles, and then okay, so that's a good. So we have 13.3 moles, right? Because we multiply, it's 40 times 2, it's 80, and 80 divided by 6 is 13.3 moles. Okay, 13.3 moles of NH3 can be made. NH3. All right, so there you go. So far, so good, right? And so now we have this answer to work with. This is going to be our n in our equals n. That's in our PV equals R in our T equation. All right, so far, so good. Everybody got that so far? So let's do, I'm going to erase all this, and then so we can have a more clean slate to work with. All right, so let's do that, or just erase everything, right? And have to erase this too. All right. Okay, good. So far, so good. And now we have, what would we say the n was? N equals 13.3 moles of NH3, right? Okay, so that's that. So now let's write our PV equals PV, the ideal gas law, which is P times V equals N, small n. I'm going to write that the same so that we don't make, just be consistent. Small n, small n times R, and then T. So we have, we got to know what the right universal constant is, so we're going to use KPA1 for that one, so we know what that one is. So let's just put in our values here. So I'm going to, once we have, so we know what P is, right? P is 142, and then we know what V is. We don't know what V is, actually, so we're trying to solve for that, so that's our question mark. We know what N is, 13.3, and then we know what R is. It's going to be 8.31. So just make sure that that's that and that's that. And then we know what T is. Well, T is in 35C, so we have to make sure we put that into K. And I know that that's going to be 308K because I did quick math in my head. And so we have that equals, right? So that's that. So far, so good. Everybody's got it set up right? So then let's solve for V. And I'm going to erase this for a second, just real quick, and then rewrite it. Well, we can just kind of do it up here, so let's just rewrite it up here. So we know that V is going to equal to 13.3. I'm going to leave the units out for right now. 13.3 times 8.31. I'm running out of room here, so I'm actually going to erase it now. So that it just makes it easier to do all this and erase. All right. So we can just rewrite it real quick, right? We have V equals, and we know that N, so that's 13.3, and then we're just going to put, that's moles, so just put moles here just to make sure we all know, times, and then R, which is 8.31, and I'm just going to use, that's just the R, so I'm just going to put KPA for right now, just to make sure we know that that's the right one, times, and then T is the 308K, right? And then that's all divided by P, which we told was 142, okay? So far, so good. All right, I'm going to make that a little bit better. So I just have a problem writing A's on this tablet. K, P, A, All right. So that's our V. So far so good. We've got all. Now it's just a simple calculator answer. So let's see what we get. I'm going to punch it out in here in a second. And if you do all the math right, you should get 240 liters. Right, because 8.31 is 8.31 kPa liters and all that divided by mole degree K. So 240 liters, right? So if you got that so far, then that's great. If not, go back and check your math or how we did the problem. Okay, so good. So let's just move on. Okay, so this is just a confirmation of how we did the problem. So here's our confirmation here. So here's our check that we did that right. So that's the number of moles using the stoic thing. And then check here, we did the ideal gas law thing. Okay, so ideal gas equation. And everything so far is checked out. So and here's our final answer. And so that's just a neat way to solve it, but I just showed you how to solve it that way. Okay, so look, if you have any concerns of how we did this, you should try it again. Go back to the slide before and try it again. Okay, so here's another practice equation that we're going to do together in the slide. All right, so the first thing we're going to do is we have to read the question. It says what volume of water is produced, and it gives me all the conditions here for all these other things. Okay, what volume of 20 grams of oxygen reacts completely at 225.0 C at 85 kPa. So it gives me the things for the ideal gas things, but I have to first do the conversion from grams to moles so I can do my stoichiometry. So I guess, again, first thing is to check balance. Let's check the balance. Make sure it's balanced. So I have 4 hydrogens, and I have 4 hydrogens over there, and 2 oxygens, and I have 2 oxygens here. So everything checks balance. Okay, so balance checked. Good. Second thing is now we get to convert from grams to moles. So we have 20 grams of oxygen. And it reacts completely, so that means it's fully reacted. I always put the 1 down here just to make sure I get the units and it doesn't get mixed up on the top or bottom. And then it says reacts completely so the other stuff is inconsequential at this point in time. And then I need to find out the volume of water. So I know that 20 grams of that times, and then I'm going to put mole here, and then 32 grams per mole of oxygen, right? Because each oxygen atom is 16, so we have, and it's oxygen, so it's 32. It's diatomic, and then we have to do the mole conversion to cross over from reactants to products, and so we have or the haves and wants, and so we have moles of oxygen have to be the ratio has to be moles of oxygen on the bottom. So we have how many oxygens? We only have 1 mole of oxygen based on the balance equation, which is 1 here, remember. If it's missing, it's just 1. So you just write that. And then how many moles of water do I make? I make 2 moles of water. So 2 moles of H2O. And so that's going to give me so if I do the scratch offs, that cancels. See that cancels this. The grams cancel. And so far, so good. So so far, so good, and I'm left with number of moles on the top of this. Number of moles of H2O, right? So let's look at the answer here. So 32 divided by 20, that's going to be 5/8, right? Because 4 times 32 is 8. Excuse me, 4 times 8 is 32, and 4 times 5 is 20. So it's 5/8, and it'll be 10/8. So 10/8 should be 10/8 should be 5/4, which should be 1.25. So let's see if that's 1.25 moles of O2, H2O. Sorry. So far so good. We have 1.25 moles of H2O. All right, so if you're good, and that's that is equal to N in the PV equals R nRT equation, the ideal gas law equation. So this is N in ideal gas. All right, law equation, ideal gas equation, ideal gas law. I guess it's the ideal gas equation at this point, so let's get rid of that and just put equation, ideal gas equation. All right, and so that's so good. That's good so far. And so now we have to put this back into the ideal gas law. So let's erase all this stuff because we already know it's 1.25 moles. And let's give ourselves some more working room here. So let's hit the erase button, think, and then do this again. And then erase everything. Okay. So we have P V equals N R T, and let's put all the stuff in that we know. So we know that we're trying to calculate this again, the volume. So we know that V equals, and let's put P on the top. Let's put all the things in. So it's 1.25. And then that's times 8.3, where we'll worry about the units in a second. And then it's 25 degrees C, which is 298 K. All right, and that's going to be divided by 80.5. All right, and the volume will be in liters at the end. And so let's erase that real quick before we put that. The volume will be in liters. Okay, and the volume is 38.5 liters. All right, so you should be making 38.5 liters of H2O gas. Right, not 38.5 H2O liters, not 38.5 liters of H2O liquid, at 38.5 liters of H2O gas. So let's just do a self-check here in a second and see what it is on the next page where he has the answers. Okay, so here it is again. So we set it up, okay, exactly how we set it up. We got the number of grams first, and we did our conversion, so the grams, and then the moles of O2. That's our right thing there. And then here's our answer that we got for the first part, and then we just put that into the ideal gas law equation, and we got that for the answer. So give yourselves a gold star if you walked through that and got that and understood it. Right, so that's good to go. You're good to go then. Okay, so this is the last slide here, and I purposely left this with the answer already shown, because this is the way we go from the reverse way, and I wanted to make sure that everybody understood how we did this first. So I left this this way so that I can kind of point and show you where everything goes, and then you can try other practice equations on your own. There are some in your book. If you need some from me, I can post some onto the website for additional practice. But if you can master the first two, then you should be able to go reverse and just go backwards, showing this with this technique I'm going to show you now. Okay, so now we are going to calculate the mass of ammonium nitrate that should be heated to obtain 100 milliliters of dinitrogen monoxide at these things. So we have to go backwards, right? So the first thing we have to do is figure out how many moles I need to make, how many moles I get at these conditions, that I have to go backwards to calculate the number of mass from the start point. So the first thing we have to do is figure out how many moles of gas there are at the conditions that are given, right? So I need to obtain 100 milliliters of gas, and these are the conditions that I get, right? So I have, here's my P, here's my T, and here's my V. We don't know N, so this is not, we don't know N. N is unknown, right? So that's question mark, right? And there's nothing here about the mass to calculate from mass to the grams to moles first. So we have to calculate the moles using the PV, using the ideal gas equation. And then we can use that back in our stoichiometry problem up here to calculate the number of grams. Okay, so it's reverse. So let's just walk through this quick. So we have all that. So let me just erase some of this stuff here. Right. So we know all the values. I'm just going to circle them and then put them back into where they go in the equation. All right, so there we go. Da, 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 da. And here's our this. So that's what we're still looking for N, so we're going to go that there. So here we go. So this is our kPa. This is our pressure, so that's that value there, which then works out to be this value here. And then 25C, well, we first have to convert it to K, and that's going to be that value there. And then the 100 milliliters, well, we could leave it in milliliters, but since our conversion factor here is in liters, we got to convert it to liters. So that's why that looks like that. Okay. And the other thing, the only thing that we don't know after all this is this value here, which we're trying to find. And if you solve the equation, you get N equals this number of moles. Okay. Everybody good so far? All right, so now I'm going to change colors of the pen. All right, and I'm going to show you. So now this mole number here is our start point for our stoichiometry problem, right? So this is my have, right? Because I just found it out, and I want the end product here, which is the grams of ammonium nitrate. So that's NH4NO3, right? I think that's right. Yep, it should be right. Okay, so I need that. So that's my grams of that. So that's my want, right? So I have this, right? So as always we do is we have, so here's our start point. I usually put a 1 here, but they didn't. And then remember the units here have to cancel. So the mole of this has to cancel with the mole of this. That's good. And then we put, there's our ratio of molar mass of a ratio of moles of ammonium nitrate to moles of Na2O3 based on this ratio again comes from this equation here, and since I have 1 mole of this and 1 mole of this, the ratio is 1 to 1. Excuse me. And then the last thing we have to do, I'm going to erase this because this is kind of in the way now. I'll just leave that there. That's all that there. So that came from that. And then what we need to do next is, I'll bring this down here a little bit closer. And then now we have to go, since this is now the moles are gone and the moles are gone, we are left with moles of this, but I'm looking for grams, so I have to convert the moles back into grams. So I find the molar mass of ammonium nitrate, which is 80 grams, and then I can calculate that and put that as the ratio here, and then so the moles go away, and I'm left with 0.33 grams. So that's pretty much the standard way. So if you can do the stoichiometry part of balanced equations, and you can do the molar, and you can do the ideal gas law one and calculate N, then you should be able to go from either the equation first into the ideal gas law, or the ideal gas equation back into the standard equation to calculate one way or the other, right? So hopefully this has been helpful, and you can see this. If you need more practice problems, we can do that. But this is pretty much the end of the lesson on this one.